James Webb Telescope stuns with bizarre new view of Saturn. Gaze upward on crisp dark nights and Saturn arrests attention through even modest backyard telescopes. That golden globe attended by shimmering icy rings beaming reflected sunlight back across nearly 1 billion miles of interplanetary void. Yet have you ever wondered what great secrets still hide behind the iconic planet's stately facade? After 4 centuries of earthly astronomical tracking, our collective perspective now shifts. Thanks to the James Webb Space Telescope's penetrating infrared vision-piercing veils at last, JWST recently unveiled a startling glimpse of the perpetually ringed world cloaked in darkness, rather than bathed in expected bands of light. Imaging Saturn in infrared rather than visible wavelengths reinforces that worlds often unveil deeper truths across non-visible hues like X-rays, ultraviolet or radio microwaves. For frigid Saturn's smog-shrouded bulk glows dark and surprisingly placid under Webb's thermal gaze, a strikingly muted inverse beacon calling curious minds to ascend and explore the unknown. So what overlooked tales do Saturn's billowing atmosphere and resplendent icy halos still tell about the planet's own past and mysteries potentially lurking on worlds hidden within its gravitational thrall? Ancient astronomical logs provide clues regarding where Webb's next revelations may lead. Let's leaf back to 1610 when Galileo Galilei first glimpsed Saturn through his meticulously ground optic lens. To the trailblazing Italian astronomer and his contemporaries, Saturn appeared oddly flanked by bulging appendages or handles touching its sides, the earliest known telescopic record of Saturn's rings in human history. Yet 17th century telescopic limitations conflated the planet's intricate halo into shapes resembling protective handles, maneuverable ears, or even separate orbiting moons, rather than the singular flat gossamer disk of ice particles we recognize today, a cosmic smoke ring arcing over 175,000 miles from Saturn's cloud tops to the innermost sea ring edge. We now understand Saturn's elaborate bracelet contains at least 100 distinct rings and delicately carved gaps, sculpted incrementally by wayward comets and asteroids torn into new orbits after wandering too close over untold eons. That represents over 50 more subtle ringlets discerned since NASA's pioneering Voyager flybys first scoped the system up close back in 1981, before Cassini's epic 13-year orbital tour revealed further unprecedented details. In fact, Cassini's high-resolution images uncovered vertically rippling corrugations, hiding within the broad rings at scales smaller than a grain of rice. These undulating meter-sized textures remain unexplained, but reinforce the sense Saturn's iconic bands still actively evolve from a dynamic fluid interplay of particles, rather than a static relic preserved over billions of years. So while Saturn's crystalline ice rings may gleam hypnotically symmetric, when glimpsed through backyard telescopes on Earth 120 times farther away, venture closer and the system bustles with textural drama against the solar system's inky black backdrops. Clearly, we have only begun unveiling the epic history still being actively etched onto Saturn's rotating orbital canvas by way of tiny tumbling tracers, no larger than dust mites, and the plucky spacecraft sampled material splashing from fractures within at least 2 worlds, where cryovolcanism and tidal heating enable liquid water oceans that could harbor life. But first, what of the gas giant planet itself? Precisely what still lies hidden beneath the planet's perennially opaque smog shrouds. This is where Webb's infrared acumen may prove pivotal by peering down through cloud layers that keep Saturn's alien weather patterns perpetually veiled at human visible wavelengths, because most images capture Saturn enveloped in creamy pastel haze, as if bandage wrapped within a hazy atmosphere hundreds of miles deep, comprising mostly hydrogen and helium gas under tremendous pressures. Yet peer into infrared frequencies outside modest human optical range, and the impenetrable atmosphere fades infrastructurally, at last unveiling a darkly shrouded globe beneath the turbulent tropospheric winds glimpsed through backyard telescopes by generations of Earth observers. It's comparable to parting a thick fabric curtain to discern structural foundations below transient wallpaper adornments. What lies beneath the masquerade? In JWST's penetrating thermal view, Saturn's bulk temperature emerges surprisingly uniform and cold, compared to the riotous visible altitude bands so iconic through ground lenses, and Webb's non-visible imaging highlights subtle temperature contrasts between latitudes and hemispheres, especially on embedded worlds orbiting within Saturn's immense realm, that each remain astrobiologically intriguing in their own right. Chief among Saturn's beckoning fleet of icy satellites looms Titan, the aptly named inaugural moon spotted by Dutch astronomer Christiaan Huygens, using his superior homemade telescope and mathematical prowess to conclusively identify the mysterious star doggedly accompanying Saturn night after night. Even through primitive optics, Huygens ascertained this steadfast celestial light exceeded any background star or intervening nebulae. Discerning its observable phases, he published the Watershed Treatise in 1656, identifying what we now call Titan as the 6th lunar body orbiting hulking Saturn. We rank this breakthrough among the most momentous astronomical revelations in scientific history. Nearly 4 centuries later, we know Saturn's megamoon Titan exceeds planet Mercury in diameter, while wrapping itself within an atmospherically prolific shroud of organic nitrogen compound haze, a dense, ruddy vapor just like Earth's own protective envelope, yet even thicker and more completely obscuring. In fact, an eerie orange photochemical smog permeates the rich, suspended particulate matter, comprising Titan's global blanket, This is likely rich solar material formed from complex interactions between baseline nitrogen, traces of methane gas, and relentless ultraviolet photons arriving from the sun. These same tholins may have spawned terrestrial life, once sufficient liquid water pooled on Earth's restive crust to permit chemical bootstrapping, because today on Titan actual rainfalls do channel liquid towards great high-latitude lakes and seas near the northern pole. But given frigid cryogenic surface temperatures averaging negative 290 degrees Fahrenheit, this liquid proves not water but rather chilled hydrocarbons, like methane, ethane, and propane, condensing from Titan's perpetual hydrocarbon-rich drizzle. Astrobiologists rank Titan as the solar system's most compelling near-term prospect for discovering extraterrestrial organisms adapted to using non-H20 cryogenic solvents in a water-sparse environment. If scientists eventually sample conclusive evidence of microbes or alternative basic biology from Titan's ethane shorelines, subsurface Antarctica may provide closer conceptual ecosystem analogues for study, until technology allows direct access into Saturn's other liquid-layered ocean moons, like frigid Enceladus, Europa, Ceres, or trans-Neptunian dwarf planets, like Pluto, Eris, and the rest awaiting outfitted spacecraft bold enough to leap over sunk developmental costs. Yet for its rich organic chemistry and liquid cycles, nitrogen-smothered Titan itself also hides another confirmed world, harboring what experts argue represents greatest volumetric astrobiological potential orbiting Saturn, tiny 500-kilometer-wide active moon Enceladus, distinguished by the staggering self-renewal power output through heating from its porous rocky core. Thanks to this heat, Enceladus spews vapor and spray like a colicky cosmic infant. You may have marveled at those iconic Cassini images showing immense geysers of churning water vapor, ice particles, and complex silica-rich organic compounds gushing into space. Above Enceladus's fractured southern polar terrain, what appears as towering cryovolcanic plumes venting for dozens of miles offers geologists true windows into subsurface conditions, wherever heated reservoirs find cracks in the small moon's icy crust. In fact, compositional analysis of salt-rich material within Enceladus's towering geysers has already offered precious insights about current bottom conditions around the most active seafloor hydrothermal openings on this highly promising ocean world. The types of dissolved gases, silicates, and metals imply pH, salinity, and temperatures reaching 90 degrees Celsius in places that replicated terrestrial vent sites teeming with thermosynthetic microbes. If even derived life manages to arise on tiny Enceladus, whether salt-loving nanobees or something more exotic, then Antarctica's ice-sealed Lake Vostok could again provide accessible jumping-off points to study implications, before cousin Jovian moons Europa and Ganymede also divulge their liquid secrets through dedicated orbital reconnaissance. Remarkably, planetary scientists lately suggest total ocean volume sloshing within little 500-kilometer-wide Enceladus potentially matches or exceeds total global water inventoried on Earth. A stunning revelation if follow-up nitrogen isotope chemistry measurements bear this out by verifying assumptions underlying prior geophysical models. Suffice to say that tidally needed orbital eccentricities keep internal heating sufficiently vigorous to potentially sustain whatever complex prebiotic chemistries or biologies time and serendipity may yield down there. Insulated below miles of crust from impinging solar or cosmic particle energies, enormous implications emerge from this tiny ice ball so seemingly insignificant by solar system metrics, yet possibly foremost by implications for life's emergence on warm worlds too. As with Saturn's resplendent yet ever-evolving rings and embedded ringlets, so should we expect chronological insights regarding its potentially life-hosting moons and worlds to continue accreting through coming years and decades. After all, organismal living systems build worlds, layer upon layer as bases for additional reaching complexity according to astrobiologists. Why should exoplanetary macrocosms unfold differently over long spans of time? For instance, every few years around Saturn northern summer solstice, temporary icy clumps coalescing from micrometeoroid dust rain and cryovolcanic tendrils out by Mimas start migrating sunward, but excessive heating past the B-ring's inner edge destabilizes these transient ice agglomerates into fresh filigrees and short-lived quasi-satellites joining the debris disk with the very fragments set loose. Hence, both Saturn's extensive ring bands and many embedded rocky denizens appear far more temporally dynamic and cyclically variable across longer timeframes than 20th century papers envisioned when penned prior to Voyager's humbling 1981 flyby glimpses. Clearly, this 4.5 billion-year-old planetary system still actively evolves and rearranges, rather than persisting locked in dynamical equilibrium since its initial formation from primordial nebula mists. This year we recognize Saturn's bejeweled rings, the orbital tilts of embedded flocks, and everything inhabiting this circumstellar disk constantly influence one another. Onward, fellow star travelers, until next we travel celestial paths where Saturnine wanderers beckon seekers towards home yet ever ancient and made new. Fear no truth nor its daughters.